And next we have the mean value theorem, whose statement is almost like what we have for Rolle's theorem, but there is a difference. Just like Rolle's theorem, we still have a function f which is continuous in this closed interval a comma b, where a and b are real numbers, of course, and a is less than b, and f is differentiable in this open interval, which is the interior of this closed interval. Then that other condition that we have in Rolle's theorem, that f also has to vanish at the endpoints a and b, is no longer present here. It may be true, it may not be true, we don't need that. And the conclusion is also different from what we have in Rolle's theorem. In Rolle's theorem, there exists a point c in a comma b at which the derivative is 0. Okay. Here, however, such a point exists at which the derivative is this instead, f of b minus f of a divided by b minus a. Note carefully that if along with this hypothesis you also have that condition that f vanishes at a and b, from this itself, from this conclusion itself, you get the conclusion of Rolle's theorem, because if f of b and f of a are both 0, then this is becoming 0. So let's now prove this. The proof starts by considering a new function, let's call it g of x, which is f of x minus f of a minus f of b minus f of a divided by b minus a, that means this thing, times x minus a. I did not get enough space to write it like that, so I wrote x minus a with this numerator itself. Next we write this. Clearly g is continuous in the closed interval and differentiable in the open interval, just like f. Why? Because f has those properties. And what do we see here? Along with f, minus f of a, which is a constant, minus a constant times x minus a. X minus a is the linear function which is differentiable, I mean it's polynomial. So that is why this combination also has those properties. Also, and this is important, g of a and g of b are both 0, which you can verify. You just calculate g of a and g of b, you will see that you are getting 0. So unlike f, I mean this may be true for f, may not be true, but for g this is true, that g vanishes at the endpoints. So now we can apply our Rolle's theorem on g. So by Rolle's theorem, there exists a point c in this open interval at which the derivative of g is 0. Now from this we are going to calculate the derivative. Now for any point x in this open interval, this is what g prime is. G prime of x is f prime of x, this is constant, so it will become 0, minus, note that this is constant, times x minus a. So you are going to differentiate x minus a, which gives you 1. So that's how you get minus this. And now here we substitute x equal to c and get g prime of c equal to f prime of c minus this ratio. But g prime of c is 0, so that's how this difference becomes 0, from which we get that f prime of c equals this ratio. This is what we wanted to show. In the next video, we are going to discuss geometric and physical significance of this result, and then we will see its corollaries, which are extremely important, and they will tell us a lot about antiderivatives. And finally, that will take us towards integration.